Yeah, so today I'll discuss some of the recent work that I've been doing with the team around how to maintain fairness in the distribution shift and whether we have viable solutions for real-world applications currently or not. So basically, to just like give an example of applications that we're going to cover in this talk. Just two examples for machine learning in healthcare. Now, the talk is focused on healthcare, but it doesn't mean that this wouldn't apply to other real-world applications. So we're looking at applications in dermatology, and you have examples here of images. So the goal of that task is to take images of the lesion, of the pathology, with metadata. These include some demographics like age, sex, sometimes skin tone, but it's not always available. It has also in some cases, other metadata like whether the person has a history of a specific condition or whether the lesion is burning or itching. But again, this is not like all data sets. And so we take that information and we want to predict whether the person has like one of 27 skin conditions. That's more like 26 plus everything else, like the long tail of those conditions. And to train our model and develop that model, we have teledermatology data from 2 states in the US. And the data is somewhat diverse in terms of the conditions that it covers. And we'd like to see, well, how that model will then perform on teledermatology images from Colombia, as well as images from skin cancer clinics in Australia. So this is kind of like the setup for our problem today. We have a second application in electronic health records. So EHRs, they represent the time series of patient interactions with the clinical system. It's all of the labs, the vitals, the medications that are recorded with a timestamp. And we take the first 24 hours of that, and we want to predict whether the patient is going to stay for over 3 days in the intensive care unit or not. And there are a lot of different types of patients in the ICU, and most systems will have only one unit. However, there's been like evidence that some of the scores that are used, not machine learning scores, but some of the, although they can be, they're overall decision trees. So I guess they're, artificial intelligence if you think about that. But like, so they have clinical scores that are like, is the patient's temperature over this or under that, then they end up having a score. And basically they have found evidence that the scores were not doing as well across all of the populations in the ICUs. And we want to avoid that the scores that we create with machine learning would replicate that pattern. So we take data from some generalist ICUs, like the medical or the trauma ICU, and we want to see whether the scores that we obtain would perform as well on cardiac ICUs. So this is kind of these two are kind of clear examples of what we would consider when thinking about robustness to distribution shift. So this is really, we have one setup and we want to think about other different types of setup. Other examples would include different hospitals, and this is the image that you have here on the right, where you have basically, so the data that we have for model development is called the source, and this is like data from one hospital on the left, and then you have images from the target, which is like this new setting that we want to cater for, like on the right, and you can see that the contrast, the colors in the images are different, and so we want to know whether the model will perform well. Now, it doesn't need to be between systems. It can also be within a system. we can think about different time periods. And there's also in EHR, there's been from Nestor et al. In 2019, a paper where they showed that basically if you train on a certain time period, then the performance of your model degrades over time. This has been repeated for another model on sepsis. Also, you can think about like different devices. When we introduce a new device, like a new scanner to take images, for example. So we can think that these are quite frequent in healthcare settings, because especially in healthcare, the data is really scarce. So we do usually like to train on one or multiple data sets and apply on new data sets. And we also have a lot of retrospective data because it's then de-anonymized and we can have access to it. But then like the prospective data might not be ready to de-anonymize, or we might not have access to it directly. And so we can only like ship the model basically for that new prospective data. So for the purpose of this talk, I'm gonna discuss like different types of shifts. The first is the demographic shift. So this is, for example, when the proportion of females is different in the target than in the source. So this is only for the demographic part of the data. Now, we also have covariate shift. So this is, for example, another device that just like captures the same image, but with another camera. We have label shift, which is difference in, let's say, the prevalence of the diseases and across the different environments. And then we have a compound shift. Compound shift is basically any combination of the demographic, covariate, or label shift. And we can quite easily see that compound shifts are going to be quite prevalent. If we take the case of, the recent case of COVID in the hospitals, then we have a new disease and it shifts the prevalence, let's say, of pneumonia, and that's a label shift. We also have new tests and new symptoms checks that we do. So we have a covariate shift, and then the people who are prioritized to enter the hospital, then this also reduces access to certain demographics, and so we have a demographic shift. So all of these actually happened at the same time when a new complex disease, for example, is happening. In terms of the current literature, we have most of the work that focuses on demographic of covariate shift. I put them together because mostly covariate is thought of as whatever is the input of the model, and sometimes the attributes, and this is especially true in healthcare, like sometimes the attributes are included as the inputs of the model. There's some work on label shift, but very few work on compound shift. And what that work usually looks at is the transfer of performance from the source to the target. But is it really what we care about? So when we look at the robustness of a model, what we actually want to know is how it's going to behave under distribution shift. And this is also helping us understand what it has learned and what type of inductive biases it's actually relying on. So basically, performance is usually like a single metric that we look at, but is that enough? And so we have looked at other factors to consider, like the consistency in inductive biases. So this is other work, and I have like other slides if we have time and if you're interested. But today I wanted to focus on the more recent work around fairness and whether fairness actually transfers across environments. So let's look at fairness under distribution shift. And what we see is when we train a model for the dermatology case and we test it on our two target data. So we have here the dermatology clinics from Colombia, and every single dot is a replicate of the model. And in white circles, you have the performance on the source, so where the model was developed. And in blue diamonds, you have the performance on the target. So you see there's a performance gap that they're not doing exactly, there's a bit of a gap here. It's not huge, but there's a bit of a gap. But what we see mostly is that this gap is not uniformly distributed across groups. And so we can see that the younger patients actually do not suffer from a really big gap, but the older patients do suffer from a really big gap in performance in the target. And if we look at skin cancer clinics in Australia, the pattern is the same, and it's actually more pronounced, where here we basically have no drop in performance for the younger group of patients, and a really steep decrease in performance for the older group. For electronic health records, we have slightly different results, where actually there's no performance gap, and the model performs even slightly better on the target, so in the cardiac ICUs, than in the generalist ICUs. But what we see is that the pattern of fairness is slightly different. So for example, we still see that in the 45-64 group, for example, like you do have a large difference in how the model is going to perform on these groups. So we see that we have different patterns of fairness in these, under these shifts. But how do we mitigate? What can we do about it? And so what we argue for is that the nature of the shift matters. And this is like a general message from the causal adaptation domain. And in this case, like if we kind of formalize the hypothesis, we can assume a directed acyclic graph. So basically thinking in terms of Bayesian causal networks. And we have 4 variables in it. So we have our attribute A, which represents demographics. We have our features X, our label Y, and S represents the environment. And here we make it quite simple. We say that the source is S equals 0, and the target is S equals 1. And whatever set of variables we consider for modeling our application, basically, if we want, let's say, performance to transfer, what we want in terms of conditional independence is that our label is independent of the environment, given those variables that we want to include in the model. Now, that only gives you performance. If you want to add a fairness constraint, you can choose between demographic parity or equalized odds. And for that, you have an additional condition, which is that the set of variables is independent of the environment, given the attribute, or for equalized odds, given the attribute and the label. So basically, if we think in terms of the relationships between these 4 variables, what we need when we see those conditions is that there are some arrows that are missing between each of them. Basically, in this paper, what we do is we try to provide an experimental way to assess the nature of the shift, because most strategies for mitigating only cater for specific shifts. So in this case, we're going to assume a causal graph of the application. It's often very simplified and not tested at all. And we're going to test for conditional independencies. And so we have 2 steps in that testing. So they're illustrated here, basically. So we assume a very, very simple graph. I've removed A just for simplicity here. And so we have our label. So let's say the condition that I have, a skin condition. Then it generates something on my skin, a lesion on my skin, and I take a picture of it. And so this causes basically the picture X. And so X is an image here. And so we have this arrow from Y to X. And what we want to know is, well, okay, in like the source, I know I have a certain relationship between Y and X, but now let's say that I want to apply my model in a new hospital or with a new device. How can I test whether my label or my features will be affected by the environment? And so the first thing I do is actually I start with the effect of the environment on my label, because it's easier, because this variable Y doesn't have any other parents. And so I can test directly whether Y is independent of S or not by doing simple like t-tests of Y in both environments. Then I want to test whether X, so my features, are affected by my environment. But basically, if I remove this arrow, but I do have an effect of S on Y, then I will end up with an effect of S on X through this path. And what I want to know is if there is a direct path. So basically, I need to control for Y, kind of like removing this path to just test whether there is an arrow here. And so we do this with balancing weights, which is something from the causality literature. And because X is an image, we actually can't do it on every single feature. It also wouldn't really make sense to look at every single pixel. So what we do is we summarize X, and there are different ways of doing that. It's discussed actually not in that Lipton paper, but in Robustness paper. And what we use as a summary for X is a classifier. In this case, it's just like our predictive model that we would do, like applying X to predict Y. And that gives us a one-dimensional summary, or whatever dimension Y has, and we can then test that more easily. So how does it help us? And what type of relationships do we see in real data? So if we go back and take the dermatology application, we are assuming this very simple graph where we are saying that the attributes A, which is just age and sex, because they're the only ones that are common to all of my data sets. So this is age and sex, and age and sex is going to influence what type of condition the person is going to have, and it's also going to influence the image. And of course, my condition is going to affect the image, so the type of lesion I will see in my image. So I start by looking at the effect of S on the demographics, because demographics has no parents and it's the easiest one. I just do t-tests. And what we see is that there is a difference between the two distributions. So on the left, you have the source, and on the right, you have the target for each subgroup. And you can see that there are differences between the two. And then I need to control for A, and I test the relationship between S and Y. And here, this is like, so within a specific subgroup of, in this case, older females, I look at the prevalence of each class just for illustrating basically what the test does. And we can see that there are differences in the prevalence. And so this is compared to the skin cancer in Australia. And we see that, for example, basal cell carcinoma, which is a cancer, is way more prevalent in the target than in the source. And this is basically what we would expect. And then the last one, we need to control for A and Y to look at the direct effect of S on X. And well, in that case, it's actually hard for me to like give examples of images, but I looked at like the summary of the images, and that showed the direct effect. And also, if we just look at the number of images that we have per case, which we actually aggregate in the model, then we see that there are way more images per case on average in the source data than in the target data. So what does that mean for mitigation? In this case, this is the EHR graph, where we have the attribute, we have comorbidities, we have treatments, and labs and vitals, and this is our target. And we can see that the environment is not affected every single variable in the graph, but it still gives like a lot of different ways for the environment to affect why. Like, let's say there's a pass here, there's a pass here, and then another one through here. So we can see that there are a lot of different ways that S is affecting our features in our label. And basically, if we, if we go back on the EHR results, sorry, animations. So what we see is that in the source, the model is quite unfair compared to age. If we just we decide that this is our fairness metric. So here we're debiasing those predictions. We're using a post-processing method, and we're saying, okay, well, now I have a fair model on my source. How does this affect the target? Well, actually, whether we're using demographic parity or equalized odds to make those predictions debiased, and this figure is around equalized odds, it helps on the source, but it doesn't help, or it makes it even worse on the target. And we can also see that the variance across different seeds is getting really large. So this really shows like some kind of instability of that signal. And that's because simply if we come back to like the different conditions that we needed to fulfill to have the transfer of fairness, we're just simply not fulfilling them in this graph. If we had a graph where we had only the arrow from S to A, so basically only a demographic shift, then actually maybe we would fulfill those conditions, and we could use fairness mitigation as a way to provide robustly fair models as well. So to frame a little bit the related work in terms of what we have seen so far is we have two kind of main lines of work. We have one line of work that gives a priori guarantees, where it's really like by looking at the different interactions between the variables and trying to find the right variables that will really fulfill those conditions that we saw at the beginning. And one of these, and maybe the most prominent one, is feature selection, where it really like just goes and builds that set of input features according to those conditions. So we can easily see that this is going to be complicated to do in practice, because it is only applicable in a number of cases. So for example, it is not applicable if you have a label shift. And because of that, it often leads to the empty set being like this set of features. So it's a bit of a trivial predictor. And so in the case of the EHR, so here, because we have a direct effect of the shift on the parents of Y, but that are not intercepted by the attribute, then basically that set is going to be empty as well. It's quite difficult to use a non-tabular data. And one way that people have been kind of like circumventing this is by using masking on the images. But masking is just trying to zoom in on the good signal and forgetting the background. But it doesn't really give you any guarantees, because it still depends on the signal to noise ratio within that portion of the image that you have selected. And there are other approaches that refer more to transfer and meta-learning. And so in this case, it's more the case of adapting in a way that is robust and fair to the new distribution. And so for that, you would require a small target set, usually actually labeled. And it does provide guarantees. So you have an example here where Schumann et al., for example, would provide guarantees in the case of covariate shift in an anti-causal graph. We have work by Slack et al. It's based on meta-learning, so it does require multiple tasks. And also, you end up with one model per environment, so that's not necessarily, like, engineering-wise, a desirable option. But sometimes it's the only option. So basically, in conclusions, fairness does not transfer in real-world applications. We've seen that the nature of the shift matters. However, clinically plausible shifts are often compound, and current mitigation strategies are not built to handle compound shifts. So there are still gaps for building fair and robust models. And we know that responsible AI is still in its early stages, where most of the work considers very simple tasks. And I can think of actually fairness mitigation, for example, typically considers a single binary classifier with a single binary attribute. And when I had to look for mitigation strategies that would apply to the dermatology case, where I had multiple subgroups for age and 27 classes, it became really quickly very difficult to find a method that would do that. And the other thing is that each aspect is typically investigated separately. So we talk about, and there's a whole community for robustness and the distribution shift, a whole community for fairness, a whole community for interpretability. And there is some interactions that's starting to happen, but it's still rather early. And if we think about it, actually, guarantees for fairness and the distribution shift are more stringent conditions than guarantees for overall, the transfer of overall performance. And so we really need those communities to talk to each other. And as potential directions for future work, some of the mitigations we can think of are actually not technical mitigations. So we can think that as a first step, we should select problems that would reduce potential harms, because we simply do not have methods that will mitigate fairness in the distribution shift. We can see that having labeled or unlabeled, but typically labeled data, at least a small amount of labeled data in our target distribution, just even to assess the shift complexity, is desirable, even if we don't want to perform fine-tuning or transfer learning. If we find that the shift abides and or verifies some of the assumptions that we're looking for, then mitigation might be possible. One of the mitigations that actually do not really fall into this framework really nicely is feature engineering. It's something that we've moved a bit away from when we started using deep learning. But more recently, there's a bit more of a it's kind of coming back in the sense that we can potentially give more direction into what the model is learning as inductive biases. And I'll just jump to the later point because it's just the most interesting one. It's just and so to give, again, to think about how we want the model to learn and what we want the model to learn and how we want the model to behave, is to give more constraints to that model. So we know that doctors learn certain things and then they learn by experience. And in this case, the models just learn by experience. So what we want is also for the model to learn those things. And it's giving clinical and like hopefully causal constraints for the model, so that we're not really trying to define another robustness or another fairness kind of distribution matching strategy, but really thinking in terms of like, what constraints do I want my model to abide by? What inductive biases do I want my model to rely on? And that should give me then a model that is, well, hopefully more robust and more fair. So of course, there are a lot of limitations with the approach and with like the work that I've presented today. The first one is that we have more of a problematic feature detector rather than defining features that would be invariant across environments. And this is quite an important subtlety, because we're really in our hypothesis test, we're testing that the features are different across our environments. And if that tests come back negative, then it's just a negative result. It doesn't mean that the features are the same. It might just mean that we don't have enough power to detect that they're different. So it means that if we rely on them, it's not going to mean that our model will abide by those relationships that we would want necessarily. We've also seen that the weighting scheme that we're using is getting more faithful when we improve the number of samples. So obviously, there's a bit of a compromise here. So you want to have a smaller number of samples to be able to do your testing, because you don't want to require too many samples from the target population, because otherwise, why not just doing joint training with that? So there's a bit of a compromise there, but like we have seen that with a few hundred samples, it's okay, but it does improve if you have more samples. We need a causal graph, and like all of these assumptions and all of these tests are only as good as the assumptions that we make for the causal graph. And as I mentioned, like the causal graphs that we have, we kind of made them up. They seem reasonable, but that's it. Basically, that's it. So we would need to really like check more for if we wanted to use that for a specific application. We also know that different fairness metrics might be relevant in different environments, and so this would need to be taken into account. So if you say, well, demographic parity is more important in my source, but equalized odds is more important in my target, then obviously you have a bit of a conflict between the conditions that you would want to have for your variables in each of your environments. Because we're using proxies, we are never really going to obtain sharp guarantees, and this is especially true for demographics. Also, everything we have is only as good as the data that we observe. So like we've seen in the dermatology case, in one data set, we actually had more data that was available, but that was only in that data set. And we were not really able to investigate, let's say, skin tone for the cancer clinics in Australia, simply because we just don't have that data. And of course, it's not because we have defined like a fairness metric that this is going to mean that we have health equity. And so this is really like trying to think about like the broader context and how we can come back to that context once, maybe even if we one day solve that issue of fairness transfer, is really like think back and contextualize all of that work. So yeah, I just want to thank all of the team and the people who have worked on this with me, especially Catherine Heller and Alexander Demore, and all of the other colleagues at Google Research and DeepMind, as well as the clinical partners. And thank you for your attention.